everyone. Afternoon. Yeah, good afternoon, everyone. We are going to finish this fella off. Before I get started, I did send a report out, a week 1 report. It was sent to your email address, either the one you used when you signed into WebAssign or your student email. So if you go looking for it, you should find it. So go looking for it later on. If you don't have it, if you've looked in your normal, personal email and you've looked at the college email and it's not there, you will shoot me an email, and on that, and shoot it to drobertson@olympic.edu. Don't do WebAssign. I never see WebAssign. It never gets to me. Anyway, send it to my normal email address, and in the email, put the email that you want to use, and I will change the email I'm using to that one, and I will send you out your report. That way, report week 2, 3, and 4 you'll get without any trouble, right? So if you don't get a copy of it, shoot me an email, tell me what email address I should use. I guess you could look in your junk folder as well, just in case it ended up there. Well, let's get started. We're going to get finished bell-shaped data today. That's my goal. And with a bit of luck, we'll get started on chapter 3 as well. Now let's do a quick recap. Can we all remember what a z-score was? Can you remember that, guy? It was a way that you could compare, a fair way to compare, say, 2 sets of data, right? Janice got this, but John got that, who did better, that kind of thing. And to remind you what it looked like, it's basically the formula was data, take away the mean, divided by the standard deviation, right? So, you comfortable with that, guy? Do you want to see an example of calculating the z-score just to refresh yourself? Okay, so suppose there was a class test and the average in the class was 57, and that the standard deviation in this class was, say, 5. And John, I'll call him John because I like small names that I can spell easily. Right, John got 63. What would his z-score be? Well, John's z-score would be his score, 63, take away the mean, and then divided by the standard deviation, right? So it'd be 63, take away 57, divided by 5, and I believe it's 1.2. And if you're really wanting to reduce the English language, do you know you can call the z-score just z, if you want to? I like z-score, but you can call it z. Are we comfortable with how to calculate a z-score? Does that refresh your memory now? Right. Now, we also did this guy. Suppose you had a mean. Well, let's keep this data. And so the mean in this class test was 57, and that the standard deviation, which is what this guy represents, was 5, right? And we know that the data was, it has, I'm going to add another name to the same thing. Right, wouldn't we say that data was symmetric, right? We know that name. It's also called bell-shaped. I think I've used that term, haven't I used that a couple of times, bell-shaped? It's the same thing as symmetric, just another name for it. It looks a bit like a bell, doesn't it? And here's the new one. I don't think I've used this name. It's also called normal. It's a normally distributed data, right? It's bell-shaped data. It's symmetric data, right? It's 3 words, same thing, right? Now, we are going to build a very special guy using what's called the empirical rule. I prefer the 68, 95, 99.7 rule. I prefer that name instead of the empirical. The empirical rule doesn't tell me a lot of information. I know that's a really ugly name, but it tells me a lot. Because what it says is that if you collected all the people in that class and you made a histogram of it, it would look normal. Well, that we already knew. But right in the center, the topmost hill, the mean lives. If you then go 1, 2, and 3 standard deviations from that mean, so you go add 5, add another 5, add another 5. And if you subtract 5, subtract 5, and subtract 5, what you get is a very accurate description of how the data is spread out. And what this rule does is it says 1 standard deviation away from the mean. So that's from here to here, right? So anybody who got a score from 52 to 62. That's all these people here. %68% of everybody in the class got a score in the range 52 to 62. Isn't that helpful? And why I like this name. If you then go 2 standard deviations away from the mean, so that's basically anybody who got a score from 47 to 67, from here to here, what percentage of the people in the class got that kind of score?
95.
95. And for completeness sake, if you do 3 standard deviations away from the mean, you get 99.7% of all the people in that class got a score between 42 and 72. Wouldn't that probably mean everybody except one person? Oh, by the way, wouldn't that one person be an outlier? Because if you are more than 3 standard deviations either side, remember the 3 standard deviation rule? If you're more than 3 standard deviations away from the mean, so bigger than 72 or less than 42, you're considered an outlier. And I think that kind of comes through here. Would you agree that if 99.7% of the data is in that range, anybody who's not in that range is extremely rare, right? They're outliers. So far, so good? Right. So let me show you what that question would look like in the homework, because you know that in WebAssign, excuse me, I lost my place a minute. There we go. Click on this. Of course, I hit the wrong button, which is classic for me. Okay, coming up on it. Here we go. Right, almost ready. There we go. So this is a version of question 11. So this is what question 11 in chapter 2, bell-shaped data, would look like.
We can't see anything. Oh, okay.
You can. I was just getting the thing set up. Now, in this question, the mean is 100 and the standard deviation is 17. So I'll go up here. All right, the mean is 100. So won't D be 100? You see why I know that's 100. Now, they're calling them A, B, C, all the way to F. For instance, that guy there is the mean of 100. Since the standard deviation is 17, won't E be 117? Then you add another 17 to get the next number. And then you add one more 17 to get the last number. And that's 51, I believe. Then you take away 17. And that gets you what C would be. If you take another 17 away, I'm not going to risk that in my head. 83, take away 17. Double check it, you get 66. And then if you take one more 17 away from that, you get 49. Right, are you comfortable about where those numbers came from and how WebAssign gets you to do it? Right, it's just the way WebAssign makes it happen. So far, so good. Now, up here, use the empirical rule to find the interval for 68%. Well, if we go back here, isn't 68 the C to the E? So what to be? 83 to 117. Can you see where I'm getting that number 83 from? And 117. So you got up here, and for my question, yours will be different numbers, right? But that would be it. Can you see how you would do the 95 and then the 99.7? Okay. I think that's going pretty smooth. I mean, once you figure out what goes where, are we comfortable about how we fill those in? Okay. So it's got this weird guy at the end that's really got not an awful lot to do with this. It's called the variance. Now, I know there was one question where there was a variance mentioned, but I can't remember if it was this class I told you about it or not. So let me remind you how it works. What do you do to the standard deviation, which in this case is 17, to get the variance? Did I tell you what the variance was in terms of standard deviation? Okay, then I'm going to tell you right now.
You have to go under your calculator to do it?
No, you don't actually need to,
Okay.
thankfully. The variance is the standard deviation squared. You just remember it and you're good. So if you ever get a question that says, what's the variance? Somebody somewhere in that question has already told you what the standard deviation is. You just need to square it. So in my case, it's 17 times itself, and it's a really big number. It's 289. So I can now say with certainty that both of my classes now know how to calculate variance. I don't think there's many questions where it's asked, but that's how you do it. So here's question 12. The standard deviation is 2. What's the variance?
4.
4.
They've told you that the mean is 56. They could have told you that the guy was called George, or that he lived in America, or that his favorite TV show was Survivor. None of which would mean one thing. A lot of people are confused by being given extraneous information. In other words, information that you do not need to use or will use in the question that's been given. Would you agree in this question, they didn't need to tell you the mean was 56 because it didn't matter. Because isn't the only thing you need to get the variance, it's the standard deviation. We don't care what the mean is, it doesn't change the answer. That question would have been a lot easier if they just told you the standard deviation was 2, what is the variance, right? Wouldn't that be a much easier question? But they do that sometimes, and I think I know why they do it. Because don't you now have to make a decision about, I know it was something to do with squaring something, but darn it, is it the mean that you multiply by itself? Or is it the standard deviation, and so on and so on, right? Answer is 4. Are we good so far?
I have a question.
Yes.
What is the variance used for?
Variance is just another measurement of how spread out things are. That's all it is. So if you were comparing two groups and I said the first group had a standard deviation of 2 and the second group had a standard deviation of 10, wouldn't you really, you'd say, oh, it's pretty obvious the second group is more spread out than the first. Agreed? Now, if I turned them into variances, wouldn't you get the same kind of impression? That's all it is. There are some more advanced uses for it, but we're never going to do those, so you don't need to worry about at least in this class, unless you do advanced statistics. So a variance is just another number that tells you how spread out things are. Not a very convincing argument, was it? It's just another way of spreading things out. That's all it does. It really doesn't get used by us anywhere except to calculate its value. That's the only reason they use it.
How does it apply to the IQ example when it's bigger than the entire scale?
It just means that this is spread out. And if there was another group and its variance was 500, wouldn't the second group be even more spread out than this one? Big variances mean you're spread out. Little variances mean that you're quite close to each other. That's all. I think you may be trying to read more than you need to for this part of the thing, right? It's just a different kind of number that indicates spread. Well, take an analogy. Couldn't you have an interquartile range of 20, right? And couldn't you have a standard deviation of 30? Aren't those two also measures of how spread out things are? But one isn't really that connected to the other, isn't it? Just different ways of doing it. And actually, that's given me a good thought. I'm going to show you another way, another number that tells you how spread out things are. Suppose I have a test and the minimum score was 17 and that the maximum score was 77. So you can imagine it starts at 17 and it finishes over here at 77, and not all the scores that go on inside. Won't tell you even how many people there are. There is a number called range. Not interquartile range, but range. And you get that by taking the maximum and subtracted, the minimum. So in this case, 77, take away 17, and that is 60. Would you agree that that number, this thing called range, isn't that also a measurement of how spread out things are? We have standard deviation, we have interquartile range, and now we have a new guy called variance. Aren't they just different ways, different numbers that tell us the same thing? How spread out things are. Does that help a little bit, Brendan? Just by saying it's one of many different ways of doing it. It's nothing, anything that special about it. But this is a cool thing. If I know the range is 60, I can actually give you an estimate. And this is the only one that you can actually do this for. I can give you an estimate for the standard deviation. It's equal to the range divided by 6. So if you want to estimate the standard deviation, just take the range, right, this guy, and divide it by 6, and you get the answer, in this case, 10, right, because it's 60 divided by 6, right? A little notation for you. In mathematics, if something is an estimate, you put little funny squiggly lines. Can you see these little guys here? You might have seen them in other places. Isn't that the symbol that OC uses? Hey. So if you're wondering, I don't think that's where it comes from. I think OC uses that because it represents a sea, doesn't it? We're near the water. I think that's why it's little wavy lines. But in math, that's what that means. Now, here's a question for you. Why does that formula kind of a, sort of a, work? And it's to do with this picture. Why am I dividing by 6 and not 4 or 10 or some other random digit? Why 6?
Is it because there's 6 values on either side of the median?
Yeah. See if you started here and you finished here, which for all intents and purposes, isn't that virtually everybody? Isn't that like your max and min? Almost, at least. Isn't there 6 standard deviations between here and here. So if you take the range and divide it by 6, isn't that roughly what one of these standard deviations would be? Yeah, that's a little side issue. It's not totally random because there is a question that uses that. If I can find one. Trust me, there's a question, I can't find it right now, but it basically says the range is 40. Well, in fact, it doesn't. It says the mean is 20 and the max is 60, right? What's an estimate for the standard deviation? So if you get a question where you're told the minimum and the maximum, and they ask you to estimate the standard deviation, first you calculate the range, which they'll probably ask you to do, but if they don't, calculate it anyway. And then divide the range by 6, always 6, and that's your estimate for your standard deviation. Are we good? Now I'm going to hit you with some really ugly stuff. Only 2 questions, but ugly. You know this nice little picture that we've got here? I'm going to take it and I'm going to put as much information in it as I can, which means that it is going to be very messy. And it's not just because I can't draw, which is true, I can't draw. Can you pretend that's just the same guy a little bit bigger? And I'm going to put 57 because in this question, that's the mean. And I'm going to put the same numbers in as we did before, 62, 67, and 72. And I'm going to go this way with 52, 47, and 42. And I'm going to put my little lines here. And what we're going to do right now is we are going to find out, do you see these little things here? I'm going to call them strips. We're going to find out what percentage each of these little strips is, right? How many, you know, of the total number of people, how many are in this strip? How many in that tiny little one at the end? And once I create this picture, you may want to keep a copy of it because you'll use it for a couple of questions, you know, because the numbers are going to change. You know, each story has different numbers at the bottom, but the picture is not going to change. Only the numbers along here at the bottom. So let's start with the first one. Can you remember that those 2 guys add up to 68%? Remember that? Doesn't that make each one of these 34%? Does that make sense how I did that one? Okay, now, if you move out to the next one, isn't that 95%? Now, somehow I'm going to use that to figure out how much this little piece is and this little piece is, okay? So I'm going to move this over to the side and we'll try and imagine what it's like. Okay, imagine you've got your guy, there's the middle, there's the first 2 we know about, there's the next 2. From here to here is 95%. Would you agree that that gets split into 2 equal chunks? Now, if you take 95, this is why this is ugly, and you divide it by 2, each piece is 47.5. Are you still with me? Now, this piece we already know is 34, and this piece here we already know is 34. So what's this piece going to be?
13.5.
And correct, how did you get it? Because you're right.
I just took the 47.5 and subtracted the 34.
Does that make sense to everybody where this piece comes from? So back to my picture and do this 13.5 that we just said, and since it's green, I'm going to keep it as green. Now, it doesn't matter what the mean and standard deviation is, because won't the mean and standard deviations only change the numbers that are on the bottom here? Won't these still be the same values? The 34s are still 34s and the 13.5s are still the 35s. Great. Actually, this is going much smoother than I thought it was going to go. Right, if you move out one more, oh dear, 99.7. Do you see the third one is 99.7? That's going to tell us eventually what this piece is and what this piece is, right? What these two little pieces here are. So let me go back to my little picture, draw another version of it. From here to here, right? These two guys there. That was 95. So what's that? 47.5, right? And 47.5. Now, if you move out to the 3, well, when you move out to the 3, you get 99.7. Now, if you split it into two pieces, 99.7 divided by 2 makes each one of these 49.85. So I know this bit, and I know the whole thing. Can you see that allows me to figure out who this piece is?
2.35.
Okay, so let's show you that in the calculator. 49.85, right, that. Take away the 47.5, which is that, and you get, in here, 2.35. Are you happy about where that came from? Bit uglier, messier numbers. I think I'll go back to being red again. No particular reason, I like color. And have you noticed that there's two little pieces still left unaccounted for right at the end? See these two little guys here? This guy is 0.15%, and this guy is 0.15%. Anybody want to have a guess at how I figured those two guys out? Because there's at least two ways I could do it.
You took 100 and then subtracted the 99.7 and then divided it by 2.
You actually said it much clearer than I was going to. Did you catch what you got there? You took the whole thing, which is 100. You take away that, and doesn't that leave 0.3%? Remember, these are all percentages, right? 0.3% unaccounted for, and then you have that. Now, you might say, well, why do I need this? Because there is a couple of questions that tell you things like this. Right. I don't like green. Right, remember, this story is about scores. So what test score do you need such that, I'm trying to use the same phrase that they're using in question 13, such that only 2.5% of the class have a low, well, what do they use? Lower or smaller? Smaller. Has a smaller, I would probably say lower, has a smaller score. So we want to know which one of these scores, because it's going to be one of these numbers in the bottom, right? 72 or 62 or 47. Which one of them would you need so that only 2.5% of the class had worse than you did? I could tell you the answer, but maybe you could think it through before I tell you.
Maybe 47 or 42.
It's definitely one of those two. So which one are you
I think
going
it's
for?
47.
Brendan's 47. What do you think, Abra?
Yeah, I'm leaning more towards the 47 because
That's good. It's right.
okay.
Right. So let's explain why it's 47. Do you know that you're only getting pieces of the puzzle? If you take 47 and everybody who's less on it, don't those two bits add up to the 2.5% they're talking about? Is that why you were thinking along those lines? Right. Suppose I phrase the question slightly different. What test score do you need to get such that only 2.5% of the class have a bigger score than you?
67.
Wouldn't it be up here? Couldn't you also ask what kind of score would you need so that 16% of the class had a bigger score than you did? 16%. Where are you going this time?
62.
Can you see that all these pieces, right? That one, and that one, add up to the 16 that they're talking about. So can you imagine that this diagram could be used for slightly more detailed questions, like, less, what score would they need to be, less than 16% or more than 16 or bigger than 5%, less than 10%, anything like that. You can use it a little bit for that. Do we feel good about how we constructed this guy? Now, when the question changes, won't you keep that entire top diagram and just say, oh, the IQ is 100. So it's 100, 110, 120, 130, right? IQ is 100, 90, 80, 70. You see, the only thing you change is the bottom number. So if you're lazy like me and you don't want to do a new diagram, maybe you could do something like this. Wouldn't that speed up your work? Now, from that diagram, couldn't I ask you the same kind of things, like what IQ score would you need to be in the bottom 16%? What IQ score would you need to be in the top 0.15%? Actually, let's do that one. What IQ score would you need to be in the top 0.15%?
Would it be 0.15?
Yeah, that's the 0.15. But what score would you need to get there?
The 136.
Right, it looks like a 6 because I can't draw well. It's 130, but I understand why you said 6. Right. There are a couple of questions where that happens, right? So you want to see what they look like so you can identify them. Let's go over and check them out for you. Okay, here is the first one. And can you see it's 58 and 2, top 5, 2.5, bottom 2.5, 16, right? That's exactly the question we've just done. 13 is an example of that. If I scroll down here, do you see that the mean is now 550, at least in this question, and the standard deviation is 50? But can you see that they do the same kind of questions again? So to be able to do question 13 and 14, you need that diagram, right? The one that we just finished a few moments ago. But once you've got that diagram, your life does become a lot easier. So I'm now going to show you in a few minutes at least the last piece of that, and we have finished chapter 2 completely. Any questions? Are we good? Good. Thumbs up. I like to see thumbs up. Okay. Let's suppose, I'll keep my numbers easy to do. Let's suppose we do IQ test. The mean is 100, right? And the standard deviation is, say, 10, right? That way I've got nice numbers. And if I build my usual guy, he looks like this, right? There's 100, right? And then 110, 120, 130 would be there. 90, 80, 70 would be there, right? That's fine. But even with the best will in the world, there's only so much you can get out of that picture, right? The 68, 95, 99.7. Wouldn't it be helpful if we could do even more than that? Suppose, for instance, I would like to know the proportion, and sometimes I'll ask you for the percentage, depends on the question. The proportion of people who have an IQ, and the first kind of question I might ask you is the proportion of people who have an IQ greater than 113. Or I might ask you, what percentage or proportion of people have an IQ that's less than 97? Or I might ask you the proportion of people who have an IQ between 93, and 101, right? The diagram that we just finished doing, right? That diagram has a problem. You can't use these numbers in it. Isn't the diagram we got only going to use these numbers? And that's not what we need. So how on earth are we going to get these proportions or percentages? We are going to use a guy called SOLE, which means life's going to get easy because it's all the number crunching and, you know, that weird area stuff where you have to look at the picture and add it. All of that doesn't matter now. For more accurate answers, the computer is going to take over, the software is going to take over and give us that answer. Wouldn't it be nice if we could do that? Wouldn't it be great if there's a nice way, an easy way of doing it? Let's see if we can make it happen then. And I'm clicking on this guy here. This is actually the last question in chapter 2, and then we move on to chapter 3. We are going to use SOLE, and each question has got its own mean and standard deviation. So these 4 questions are totally independent of each other. And so in this one, it's 430. Right, so I'll write that down. We want to be below, that's less than 430. Okay, that's good. The mean is 500, right? Oh, let's do my numbers. Why do I need to use this? I'll click on this. Right, I'm going to shrink this guy down a little bit so you can see it. Now, do you see our nice little normal distribution shape with all the usual numbers underneath? We don't worry about those right now. And I would go and make sure that this says normal, which it typically does. Depends on the question. In ours, the mean was 100 and the standard deviation is 10. And my first question is, what proportion or percentage of people have an IQ greater than 113? In this little picture here, do you see that's a less than? So if I click on right-tailed, that's the one that you use if you want to find percentage of people bigger than something. What would I use the left tail for?
Smaller than something?
Yeah. And what do you think I'm going to use the between for?
Between stuff?
Between, that's the easiest of the 3 because the word is in it, right? Now, back to my question. We want to be more than, bigger than, whatever way you want to phrase it, right tail. And we want it to be more than 113. So you go here and you type in 113. See a little picture of it? Just for free. Now, when I click off that, there is the answer as a proportion. Suppose they wanted the answer as a percentage. Wouldn't that just be 9.68%? That's cool, isn't it? That you can get it. Basically, the software does it for us. Suppose I would like less than 97. Well, left tail, go over here, change this to 97. And can you see that about 38, well, 0.38209 as a proportion, or 38.209% if you want to go percentages, have an IQ less than 97. And the third question I had was a between one. So you want to be between IQs between 93 and 101. So over here, you always put the small one. And then over here, you put the bigger number. And I put in definitely the wrong number there, too many digits. Yeah. Does that look between 93 and 101? Does that look about right? You can see it visually. And can you see the answer is, as a proportion, 0.29789. And if they want the answer as a percentage, how about 29.786%? That is remarkably powerful. Doesn't that mean that as long as I know the mean and standard deviation and that the shape is roughly a nice hill, symmetric, can I get any percentage that I want, or any proportion that I want? I can tell you how many people in the entire sample are bigger than 110, less than 82, between 85 and 87, right? Anything I want, simply by using this piece of software. Cool. Right, before we leave, that is, there's only one question, unfortunately. I wish there was more that does that. Let's look at some notation, and that's all how you write things down. In English, you would say something like, what proportion of people have an IQ greater than 113? That's what it would look like in English, right? So you would say something like, what proportion of people, or the sample, depends on the story, what proportion of people have an IQ? And then you would use words like greater than, more than, things like that. I'm going to use more than because I want to. 113. That is a lot of English, right? This is the notation that we use. That means the same thing as this. What proportion of your people have an IQ greater than or equal to 113? What would this one mean? If I just wrote that down, because you're not always going to get questions where everything's given to you in English, right? They're going to be in later sections questions that look like this. What would that be in English?
What proportion of people
have an IQ
less than 101?
Yeah, you were doing a double team there. Yeah. The hardest one, or the weirdest looking one, would be this one. That's how you write mathematically numbers, IQs in this case, between 93 and 101, right? Can you remember, I don't know, 99 or somewhere where that would appear, right? I think these two are really clean. It's pretty obvious, you know, bigger than something, less than something. This one's a bit clunky, but it means between, right? If you ever see that, it's between. Are we cool with that? Now, if the question says percentage, you can use the same number, but I've forgotten what my answer was. So can we pretend, oh, I do know the answer, that this guy as a proportion was 29786. But if the question said percentage, wouldn't we write the same thing down, but just write that? Proportion is a decimal between 0 and 1, typically. Percentage is a number, in our case, typically between 0 and 100%. Are we good? Any questions? I like it. No questions.
Quick question.
Yes. Go.
You said the point, the decimal is the proportion.
Yeah.
And then okay. And then the other is percentage.
Yeah. I know the percentage has a decimal place in it, but you know what I mean, right?
Okay.
Proportion is 0 point something. Percentage is clearly a percentage. And aren't they both the same thing, just different ways of writing them? 0.5 is the same thing as 50%, for instance. Okay, then now we are going to do the beginnings of our next chapter. So there's going to be a fair amount of notes in this. So we're going to be looking at chapter 3. We're going to be looking at, I'll put it down here, it's such a big heading. Patterns in scatter plots. And a thing called correlation. Okay, let's start right at the beginning. because nobody, well, I don't know what your background is, what you've seen before. So some of this you might be saying, yeah, I knew it. I've seen it when I was 12. I've seen it 100 times. No biggie. But for other people, it's not so obvious. So what I'm going to do is I'm going to start with a scar plot. And you have an X and a Y axis, and it's a bit like plotting coordinates. A scar plot is a way to represent data that is given in pairs. So I want you to imagine that we got some animals, and we took their age and we measured their weight, right? And just so I'm making up, I wouldn't even tell you what the animal is because it's made up numbers, right? So nothing, 1 pound, 2 pounds, 3 pounds, 4 pounds, 5 pounds, the x-axis. And this here is the age of the animal, and it's in months, right? So we take a baby, you know, it's orangutan, right? And we measure their age against their weight. I think I said weight. Did I say weight? Matters, I can change it. Yeah, weight. So each one of the dots that I'm about to put represents one particular baby animal. And I guess I should have scales here. So and this is going to be in pounds. So for instance, that's 0.2 pounds and 0.4, 0.6, 0.8. So one baby, whatever you call it, weighs that. And then you have each of these dots represents one particular animal, right? So you have a whole bunch of them, and that's what a scatter plot looks like. Each one of those dots represents one piece of information. For instance, see that dot there that I'm pointing at? Wouldn't that be one animal? He was 1 month old and it weighed 0.2 pounds. So it's age, right? And its weight. You see why it does look like coordinates, doesn't it? So we are now going to be looking at data that isn't a single number, but a pair of numbers. And each number might represent something totally different, right? The first number here is age. The second number here is weights, right? One of them is in months and the other is in pounds, right? Totally different units as well. But nonetheless, we can plot them. That's what a scatter plot. Have you seen scatter plots for whatever reason somewhere, whatever? Right. So we are going to look at a number of different terminologies that we use when we deal with scatter plots. For instance, here's my first one. We tend to look at a term called association. Association can be positive, negative, or none. So here are little baby scatter plots with no great information because it's just the idea. Can you imagine that you've got some data that looks like that? You've got some data that looks like that, and you've got some data that looks like that. If you have positive association, it means basically that the data is going uphill. Would you agree it's not very clear, but in general, it's an uphill journey. This one's probably a little bit better. Would you agree that's a downhill journey? And would you agree this one is going nowhere, right? This is positive association. This is negative association. And this is none. So if I say to you, oh, I've just finished doing a scatter plot and it has a positive association, do you get a feel for which one of these three pictures, very roughly, the data looks like? So we're using words to try and describe something that is visual. Now, second thing I'm going to add in is strength. So what I'm talking about here is how strong is that association? So let's take positive, for instance. Can you imagine that it's positive and it looks like this? And then it's positive and it looks like this. And then it's, oops, I need a bit more room for the last one. It's positive. But it looks like this. Although these three are definitely positive, at least I tried to draw them so they look positive, right? Maybe that one's not very clear, but can you pretend it's positive? When we talk about strong, strength, we use words like strong, moderate, and weak. Would you agree that this guy is what a strong positive association looks like? This guy, oops, is what a moderate one would look like. And this is what a weak would look like. I'm not doing it, but couldn't I do a negative the same way? Would you agree it makes no sense to say that there's no association, but it's strong no association, moderate no association, or weak? If you've got no association, right, if there's none going on, don't these terms are irrelevant, right? You would never use them. Okay. And then we very often use a thing called shape. Now, again, just because I don't want to do too many versions of this, this also works for negative as well. And so I'm doing a strong one. And that one's meant to be strong as well. Would you agree, as badly as I've drawn that, wouldn't you agree that this data is linear? Linear means straight line. So the two terms that you'll typically see here is linear. And the next term I do not like, I wish they didn't do it, but I'm going to have to tell you because they use it in the book. Curvy linear. I wish they just called it curved. I honestly do. Because doesn't curvilinear look like it's something to do with straight lines because there's a linear bit at the end? But curvilinear just means your data is curved. Would you agree that data is more curved than it is straight? Great. Now, let's go back to this guy. What kind of association does this have?
Positive.
Agreed? Positive. What kind of strength? Sometimes that's a judgment call.
I'd say strong.
Okay. And if you want to go moderate, I'm not saying she's wrong, but any you want to go moderate?
Sure, I'll go moderate.
Go moderate. You know, you can qualify it. If you really are on the fence, couldn't you say moderately strong? So if it's definitely strong, go for it, right? If it's definitely moderate, go for it. My gut feeling is that maybe one, maybe the other. So I would probably qualify that and say moderately strong, but that's me, right? So you can qualify that. You're not allowed to qualify the next one. Is that linear or curvilinear?
Linear.
Linear.
I don't think we're going to argue with that one. Agreed? Things look straight or they don't look straight, right? I think we can decide. So can you see this terminology? We can actually describe a scatter plot. So I'm going to write down a description of a scatter plot, just using the words that we have, and see if we can come up with it. And I'm going to put it in any order I like. It's curvilinear. It's strong. And it's negative. I'm going to give you a minute to draw some really baby dot scatter plot that looks like it. You don't need to worry about details. You know, do one of these kind of pictures, and we'll see if we agree at the end. So you got 1 minute, no rush, go for it. Okay, now I'm going to do my best version of this and see if we agree. Since it's curvilinear, but it's also negative, doesn't that mean it has to come downhill like a children's slide, right? So as the x's get bigger, the y's get smaller. So what that tells me is that it's coming down pretty much like that guy, right? Did you get that feature in your scatter plot? Right, that's feature number 1. So that's curvy. Well, that's actually 2 of them. Isn't that curvilinear and the negative taken care of? I'm going to keep the dots. Would you say that's pretty strong? You might have better than me, but that's pretty strong. So we now have quite precise words that we can use. So only by using 3 words, didn't I get you to create a picture that looks not unlike mine? So words that represent visual things can be helpful. Now I'm going to give you some stories. And you have to decide between positive, negative, or none. Just the association, right? So an example of that question might be something like this. We collected data on the age of 20 kids and we measured their weights. So you'd have age against weight. Positive, negative, or none. What would you expect? Their ages against their weight.
Positive.
Positive.
Right. Would you agree the older a kid gets, typically the heavier they get, right? Now there's exceptions to everything, but if you got 2,000 kids, then it'd be more clear. How about the miles of running per week and the time it takes you to do a 5-kilometer run? So they got a whole load of people that did, yeah, you're pointing the right way, I think, Eric. Would you agree that the more miles per week you run, the more you train, wouldn't your time to do the 5K go down?
Yes.
So you can imagine, you know, number of hours that I train and time. Well, if I train a lot, I'll probably end up, you know, the people who trained a lot are probably down here, right? Shorter time. The length of your forearm, God, what a stupid question. Anyway, it is in front of me, so I'm reading it. The length of your forearm and the length of your foot.
Positive.
Bigger forearm, bigger feet.
Negative.
I'm not disagreeing with you. I'm just not sure. Is the honest answer.
I would assume in most cases it would be positive,
Right.
but not, I guess it would be weaker association.
Yeah, it'd be weak, right?
Like maybe if
I-
somebody broke a
right.
growth plate and one of their foot is stunted or something.
Yeah,
But like that's
with
the only
the- with-
exception.
yeah, with the exception of people who have some illness, I think I would say that that is probably positive. I agree with it. It took me a little while to convince myself, but I think as long as we said it was weak or something, would probably be good, because, you know, certain parts of your body don't necessarily grow the same way other parts of your body, right? That was bothering me. The next one, for cities in United States of America, the x-axis is the proportion of adults who receive flu shots. So, right, they collected data on, say, 100 cities in America. The percentage who got flu shots is the x-axis, and then the percentage of people who caught the flu in that city is the y-axis. What would that look like to you?
Probably negative.
Right, the more people who got the flu shot, less people catch the flu. I would say negative. I don't know how strong it is. I hardly guess unless I was into that kind of information. So let's jump over and look at some of the visual questions, because they're really not anything I can do easily. Right, here's a scatter plot. Positive, negative, or none?
Negative.
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 Right, now do you see how that there are 4 answers, but only one of them's right? But unfortunately, there's 2 negatives. So we have to pick the negative that describes why it's negative, right? Now the top one, number 2 here, right? It's a negative association, and they say, as the percentage taking the test increases, the average of the SATs decrease. Would you agree that's correct?
Yes.
Yes.
Now, if we go to this negative, let's see what's wrong with it then. As the percentage who take the test increase, the average SATs increase. Well, that's definitely not what's happening. Can you see that that is wrong? So one answer is right and the other one is wrong. Now, is this linear or curvilinear? Now, that is a bit of a, I hate curvilinear, linear questions. When the data is so weak, would you agree it's all over the place? And so the question is this roughly, and everything in the world is always roughly, is this roughly a straight line? Or is this roughly a curve? I know the right answer, but I don't think it's a clear right answer. I wish they had made it much more obvious, right? But they didn't. So what do you think it is? Linear or curvilinear?
Is that a curvy?
Linear.
Right. And I can understand why you get both answers, right? Why someone said one and the other. The answer that they're giving is linear. Now you might say, but I can see a curve, because if I look hard enough, can you see there's a curve that goes something like that? Right? No, I'm not. Why is it linear? Well, if you think about it, isn't this line pretty close to everybody? Right? So sorry about that. I don't pick the questions. WebAssign does them, but they think that is linear. Yeah, okay, it's linear, right? Oh, here's some questions from the scatter plot. Let's do them. I forgot to do things like that. About what was the highest average SAT score? So each one of these dots is actually a state. That's interesting. So what's the highest SAT score? And the highest SAT score would be that dot there. Would you agree?
Yes.
Yes.
Now, I could try and guess it, but you know, if you click on the thing, it tells you. And can you see what the highest SAT score is?
605.
Yeah. You see it there?
Yes.
So, yeah, so if you need to read off something from these diagrams, because these scales are so vague, it's hard to tell, just click on the thing and read off the number, you'll find the guy you're looking for. What was the lowest one? Well, it's that one there, isn't it? It's just a little bit, so that would be, what, 470 according to them? So we would be saying it's 470. And then what percentage of graduates took the test in that state? Well, if I click on this one, what percentage would that be? Well, it's 80 something, so it should be in here somewhere. Say that number again, 83, that one there?
Yes.
Okay, so 83 is. Yeah, and it makes sense. And that's an interesting set of data there. Let's just look at this data for a few minutes before we move on. If every single one of these dots represents a state, different states obviously have different rules about who takes the SAT. Would you agree that some states, almost every high school student takes it, right? 83% is pretty much everyone, right? And in some states, almost nobody takes it, right? Like 5% of you take it.
Yeah.
Right. So can you see why this data would not be good to try and compare states and say, our state is better than yours? Because let's just pretend that this dot up here, one of these dots here, was Washington State. We could say, hey, the average SAT of our students is 580. And I'm picking a state. New York is only 480. We're better than New York. See how good our education system is. Do you see that's an unfair comparison? Because I'd make an assumption. If only a few people take the SAT, isn't it probably the brightest and best? Wouldn't that be a big explanation for why that SAT average is so high? And if you have everybody take it, isn't that pretty much going to guarantee that your average is going to be lower? Because won't you get really good people? The vast majority are average, right? And a few not so good. And that drags it down. So when people compare states, don't you need to keep in mind, are you comparing like with like? See, if you had a test, I know it doesn't exist, but suppose you had a test like the SAT, where every single high school student took it, then wouldn't that be a fair way to, looking at the average, a fairer way to compare states? Because everybody takes it. If you self-select, not good data. Don't even think about using it. I like that question. Well, for me, I like that question because it does show. You can imagine what an unscrupulous politician does. Suppose you are in favor of higher taxes and you want to come on TV and say 90% of adults are in favor of higher taxes. See, I've got the backing of America behind me. Well, I could tell you a couple of ways to get that kind of data. Couldn't I make sure that I only ask people who don't pay any taxes at all? Hey, I don't pay them. Yeah, double the taxes. I don't care. I'm not paying them anyway. Right? I don't pay taxes. That would be one group. Couldn't you only ask people by putting a piece of extra information next to it? Like, we want to reduce homelessness. And to do that, we need to increase the taxes so we can build affordable homes. Right, see if you put that bit in the sentence, wouldn't a lot of people say, yeah, I don't like homeless people. I don't mind paying a bit of extra tax because, you're going to build houses for people that need them. I'm cool with that. Can you see by doing the question that way, but not telling people that's what you asked? Couldn't you get answers of any kind? It's a well-known fact that people in America are in favor of free stuff. And they're also against paying for free stuff. So if you ask them, do you want this for free? Yes. If you ask them, do you want to pay for this so someone else gets it for free? They tend to say no. And that's human nature. So I pay very little attention to polls that tell me Americans think this. Because if it's a politician that's asking that question, can you see how easy it is for them to twist the information? So I kind of take the assumption that that's what they've done. And yeah, you can tell I don't like politicians, can't you? Just a little bit. The way my brain works is I assume that they're telling me lies, and that way I don't get disappointed too many times. We got time? Yeah, we got time for this one. Here's another scatter plot. I'm going to make my own questions up because I like the data. Right. Positive or negative?
Positive.
Positive.
Agreed. Linear or curvilinear?
Linear.
How strong do you want to make this one?
Moderate.
We could
Moderate.
go moderate. Anybody think weak might be better?
I think there's a couple outliers that might make it weak, but I think it's closer to moderate.
Okay, so moderate, some of you weak. Can we split the difference and say moderately weak? That'll keep us all happy.
Can
But
we
if you-
do that?
Only if they give you the choice. If they don't
Oh,
give you the
okay.
choice, you have to pick it from the choice, right? But if I was doing it on my own and there was no test question associated with
So it all depends on the question then. Got it.
Yeah. The question will give you choices and you can only pick from those choices. I don't think I've asked it yet, so in case I haven't, linear or curvilinear?
You asked and we said linear.
Okay, then we are good because I agree with you. Now, I'm going to have to, this is going to take a little bit of time, but I want to do this in one more thing. So I'll try and do this quickly and maybe on Friday I'll go back to it again, but at least to give you a shot at it. Here is a whole load of data, the kind of data that you get from scatter plots. Problem with this data is I don't care about the city, that's just information that they're telling me. But I'm interested in latitude, August temperature or January temperature. But to do a scatter plot, I can only have two axes, right? I don't want to do three-dimensional, that hurts my brain. So I want you to pretend that January temperatures aren't there. So it's the latitude, you know, how not to south latitude against August temperature. Okay. My guess would be the further south, the higher the temperature. Would that make sense? Vegas is to the south, right? Some places to the north. That's not perfect because east-west kicks in. And I've got all this data, and I would like to know which of these scatter plots it is. So when I hit use salt, a whole load of data appears, right? Here it goes. And I would like to do a scatter plot, not by hand, but using the software. If you click charts and graphs and you hit dot plot, and then pick latitude. Oh, why is it not allowing me? Oh, that's dot plot. My apologies. Scatter plot. Latitude against August temperature. And God, that's still too big. Okay, can I shrink it up? There. Can you see the scatter plot now? One of the four pictures is that scatter plot, and you can pick it. Would you agree this is negative?
Yes.
Would you go linear?
Yes.
In case they ask that. We're going to argue about this because you lot have got a better opinion than I have. Probably more accurate opinion. I would say that thing is moderate to weak. I like qualifying myself because it's hard, right? If I had to go for it, I would probably go moderate. But some of you might say it's weak. And hey, you get 5 guesses, right? So if it doesn't want the first one, then you're going to get it right in the second one. So it's not a biggie. And I said there's 2 things I want to do. So here is the last thing I want to cover for today. While I'm getting this set up, will you all, instead of saying hi, you might have already done it, so don't do it again, but will you do your last name space first name? Because it's going to make it easier for me to do attendance, right? So it's Oaks space Abra, right, for instance. And if you've done that, then don't bother with doing it again.
I think everybody's doing it again, so you know.
Well, I'll just have duplicates, I guess. I'd rather you only did it once because I have to then kill off all the duplicates so I can count them and then put them in order, but never mind. Okay, imagine I have got some data, scar plot, and here we go. Boom, 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 boom. There. Positive, linear, and strong. Can we all agree on that? Get it out of the way. We are going to look at a term that we've used before. Outlier. Now, an outlier in the context of a scatter plot is a piece of data that is in some way separated from the main bulk of the data. What I tend to do with data is I draw a sausage around it. There. See my sausage? Inside my sausage is all my data. That data does not have any outliers. We agree everybody is pretty close to everybody else. It's pretty skin sausage. Skinny sausage means strong. Fat sausage means moderate. Huge, big, bloated sausage would mean weak. You see how my sausage idea just turns into how big my sausage is, right? Now, outliers. Suppose that was one of my data points. I'm making it nice and big. Can you see why that qualifies as an outlier? Does that make sense? This guy is an outlier. And remember, outliers can be male or female. I use the word guys in an asexual way, right? Doesn't associate with either sex. Are you happy with that guy being an outlier? Right? Is that guy an outlier? Yeah. Most people are pretty comfortable with the outliers that are over here and over here. This one you might disagree with, but nonetheless, it's still an outlier. That guy is an outlier. But isn't he in the same straight line as all the other data? You see that? He's in the same direction, the same pattern. But why is that guy, this one here, what makes him an outlier?
There's a lot of space between it and the rest of the data.
Agreed? A little bit less room, but can we call that guy an outlier as well? So basically an outlier is anybody who's not in the sausage. Do not write that down because people will laugh at me. But Mr. Robertson said an outlier is a guy that's not in the sausage. And they'll say, what? You know, I'm using terms that are not official, right? I'm just using a term to try and get you a visual idea. Are we good with that? Right? I think that's a good analogy, isn't it? Sausage, outside, inside. We're good. So that's what an outlier looks like. Outliers are horrible things in scatter plots because next time we are going to deal only with linear, not curvilinear data. We're only going to restrict ourselves to linear scatter plots. And when it's linear, can you imagine that there'd be a straight line that could pass through most of the data points? Can you imagine you'd want to know that straight line? Because you could use that straight line to do predictions and things. Well, why are outliers horrible? Outliers, even one outlier, can make this straight line move around. See this outlier here and this one here? They don't tend to cause much damage because aren't they flowing in the general direction of the data? But can you see what this outlier could do? What in fact it does is it bends the line like it was a magnet. And if there's a couple of them, it could bend it even more. Even although it's only one number, a badly placed outlier could make the equation of the best fitting straight line a very bad fit. And so when you collect data that's made up of two, pairs of data like this, you're going to do it in a scatter plot, and then you're going to say outlier, right? Like you're going to point at it and you're going to say unclean, right? We don't like it. So let's return to this guy. Is there anybody in that data set that you have a suspicion could be an outlier?
Yes.
Could you give me its X coordinate and its Y coordinate, roughly?
X would be like 33 and 92.
So you're telling me that that dot up there looks a bit like an outlier?
Yes.
Right? I wouldn't argue with it. It could well be. I'm not saying it is, it's not. It's at least a candidate, agreed? It could be. I can see one more that I would be thinking is a candidate to be an outlier.
With 38 and 64.
Right. Now, can you imagine I had a little magic eraser and I rubbed out that data point, right? I threw it away. And I went down here and threw it away. Wouldn't the rest of the data be much stronger because of it?
I think there's
Yeah.
actually one more.
Yeah,
Oh.
26
Yeah,
and
it's 26
26 and
83.
83.
I missed one. Oh, this darling over here, is that the one?
Yeah.
Yes.
Yeah, you're right. If I kicked that one out, wouldn't the data look even better? Right. Now, the problem with throwing things out that are outliers, if you're unscrupulous scientist, couldn't you throw away enough data so that a curvilinear data started looking very linear? And therefore, you would be modeling what's going on with a straight line instead of modeling it with a curve, which would be more correct. If you were unscrupulous, couldn't you throw away data that doesn't agree with what you think the truth is to make the data that's left seem more convincing because of that?